All right. So what I research here at the lab is one of the most extreme plasmas you can create, which is a dense plasma created by an intense laser. Now, these are really interesting systems with potentially lots of applications, but they're really hard to measure because they're so small and exist for such a short time. So fortunately, we can apply some everyday physics to learning how these plasmas move. And the mechanism I'm talking about here is Doppler shifts, which maybe you are familiar with if you've ever been on a road and an ambulance screams by you with its siren blaring. That siren is, of course, emitting sound waves. And as the siren moves, those sound waves can stretch and compress, changing the pitch that we hear. So if the siren is behind you and it's coming towards you, you hear wee woo, really high pitched because the sound waves are compressing. But as it flies by you, you hear wee woo, as it falls in pitch, right? And that's the sound waves expanding and stretching out as this ambulance goes further away. And so the reason that you can hear that so well is because the ambulance is traveling about 10% the speed of sound. And so because it's such a fast fraction of the speed of sound, you can really hear it very well. Now, for my research, we're going to use a different wave. We'll use light, not sound. Also has a wavelength, but the speed of light's about 1 million times faster. So we're going to need to find a plasma that's moving really fast if we're going to want to study this. Now, when we take metal foil, say some kitchen aluminum foil like I have here on the slide, and we hit it with a really strong laser, it actually does move really fast. That laser blows off a lot of material. And so if I study that with an instrument that can see the wavelength of light, I actually see two different wavelengths. I see a main peak that's sort of centered at the main wavelength you'd see if the plasma weren't moving at all. And I see another wavelength that's actually compressed a bit. It's just the same as the ambulance. Now we're squishing that wavelength because the plasma is flying towards us. And I can see based on where the first peak, the tall one, and then the second peak to its right are, the separation between those peaks gives me a speed of about 0.1% the speed of light. So it's a much smaller fraction than the ambulance, but it's pretty amazing that this is something we can see and record with our instrument. And I'll note one more interesting thing we didn't expect to learn here, which is that we're not seeing the plasma gradually speed up and start at still and accelerate gradually. No, we're seeing zero, a standstill plasma, and we're seeing 0.1% the speed of light, this finite speed. So this is as if this ambulance is sitting there, siren blaring at a red light, and suddenly the light turns green, it slams the gas and accelerates right up to 70 miles per hour, then just cruises right at that speed. And so we're still trying to learn why is it that the plasma does this when the laser hits it, but it's really fascinating, and I'm just happy to be able to share this data with you today. So thank you very much for coming.